All right, we are in section 2.3, and we're going to talk about properties of functions. We're going to start talking about even and odd functions. So the definition for an even function is that when you plug in negative x into the function, you get f of x. And if xy is on the curve, then negative xy is also on the curve, and it's symmetric with respect to the y-axis. If we're talking about the definition of the odd function, f of negative x is negative f of x, so a little bit different than the even function. If xy is on the graph, then negative x, negative y is also on the graph, and it's symmetric with respect to the origin. So let's get right to some examples. So here is an even function, and if we move kind of some pair of mirrored points around, notice that for opposite x values, we get the same y values. That's the definition for an even function. Doesn't matter where we go on the domain. Here the domain is all reals. If we plug in opposite x values, we get the same y values. And we should be able to show that algebraically as well. So if we take the original function and we plug in negative x for x, an absolute value of negative x is the same as the absolute value of x, so we can do that replacement. And then if we multiply out the negative x to the fourth, 4 negatives becomes a positive. And look what we have. We have the same function that we started out with. So f of negative x is f of x. It's an even function. We've shown it algebraically. Okay, here's another one. This is another even function. Again, graphically, we can see that for this function, if we take opposite x values, we get the same y value wherever we go. And we should be able to show that algebraically. So g of negative x, we plug in negative x in place of x. And if we write it out, negative x times negative x, well, that's a pair of negatives, so we get a positive. And what do you know? We wind up with g of negative x is equal to the original. That's the definition for an even function, and we've shown it algebraically. Okay, here's another one. This one is an odd function, and here notice that when the x values are opposites, the y values are opposites. If x values are opposites, y values are opposites. And we should be able to show that algebraically. So if we plug in negative x and then write everything out, at least with this first example, multiply everything out. Notice in the top we have an odd number of negatives, so we get negative 2x cubed. And the denominator we get an even number of negatives. Notice that that's the opposite of the original, and that's the definition for an odd function. And we've shown it algebraically. Here's another one. It's another odd function. When the x values are opposite, the y values are opposite, no matter where we go. And we should be able to show that algebraically as well. So if we plug in negative x into the function, notice that if we take the cube root of a negative, we can move that negative outside. We get a double negative. Notice that that's the opposite of what the original function is, and that's the definition for an odd function. And we've shown it algebraically. Here's another one. So here, wherever we go, the x values are opposites, then the y values are also opposites, and so this is another odd function. Okay, so next we want to maybe take a look at just a couple functions that are neither even nor odd. And so here, if you can just find one counterexample, you can say it's neither even nor odd. And so we move that around. Notice that these output values are neither the same nor opposites. Here's another one where if you can find a counterexample where the y values are neither the same nor opposites, then it's not going to be even, not going to be odd. So there's a counterexample. And here it's a little harder to kind of prove that it's neither even nor odd, but you can still plug in negative x and simplify. And we get negative x cubed because we get an odd number of negatives. And notice that the first two terms are opposites, but that last term is the same, and that causes a problem. It means it's not odd, it's not even, it's neither even nor odd. Okay? So moving on, we're also going to be talking about increasing and decreasing functions. And the definition for an increasing function is just as you are going further along, your new value is larger than the previous value. And if it's decreasing, then the new value is less than the previous value. It's constant if the function values are the same on a given interval. So that's our definition. And we're also going to be taking a look at local extreme values. So a local maximum happens when an f of c is greater than or equal to all the values around it. And it's a local minimum if the f of c is less than or equal to all the values around it. And then the last thing we will incorporate are absolute extreme values. They're sometimes called global extreme values. And it's very similar to the local extreme values. If f of u is greater than or equal to everything around it, then u f of u is where we have the max. And v f of v is going to be where we have the min if there's nothing that is less than it. So here's an example. And we label the endpoints. We start with the domain, which is x equals -2 to x equals 5. The range is the least y value to the highest y value. And it's increasing on the red part of the graph. It's decreasing on the green part of the graph. Notice that we include the endpoints when we describe increasing and decreasing typically. And if we're looking for local extreme values, we describe them by y values. So local max of y equals 1 at x equals 2. We also have some local mins. And the local min is y equals -4.906 at x equals -1. And then there's another one in a little neighborhood of y equals -1 at x equals 4. And then for the absolute extreme values, we have to include the endpoints in our analysis. So notice that. Okay, this one's a little trickier. So this one, the domain and range, they're relatively obvious. We include those endpoints. It's increasing where it's red, where it's kind of going up. It's decreasing where it's going down. And then it's constant on those purple sections, right? And again, we include the endpoints typically when we were describing these things. Now let's talk about some local extreme values. So local max happens, it's at y equals 1, but it happens on a region, right? It's not just at a single value. So it's for all of those x values. And then similarly, for the part down below, we have local min of y equals -1, but it's not at just one point. It's on a set of points. And then from those, we look for our absolute max, our absolute min from our candidates. This time it's not at an endpoint. It was from those local extreme values. All right, here's another one. The domain is -5 pi over 2 to pi over 2. Range is -3 to 3. Notice we're including the endpoints. It's increasing where it's red. It's decreasing where it's green. Use your intuition here. And then if we start talking about some local extreme values, we have local maxes of y equals 3 at 2 different x values. We have a local min at one spot, kind of in the middle of the domain. And then the absolute max comes from the local maxes. Absolute min comes from the local min. Now, take a look at this new function. It's a little bit different. Notice we have some missing points. We have some missing points. So the domain is different. We're not going to include x equals -2 pi, x equals -pi, or x equals 0. And that also makes the range a little bit different. We don't include -3 or 3. Where we describe that it's increasing is also a little bit different because we can't include the endpoints. And it's decreasing on some of this a little bit different. So compare that to the previous problem. There's no local max, and that might be a little surprising, but there's just no local max. And if we try something like close to x equals 0, like 1/10 or 1/1000, maybe that's where the local max is. If we zoom in on that pair of points, or one of those points, we notice that there's always something that's bigger, right? If we were to get a little bit closer to 0, we could get something that is bigger. And so if we try 0.01 or 0.001 or 0.0001, there's always something that's bigger. So there's no local max there. And similarly, there's no local minimum. And if there's no local max, there's no local min. And the endpoints don't give us an extreme value. There's no absolute max, and there's no absolute min. Okay, another example. Here, notice that there's an arrow on that left, so it doesn't stop. The graph doesn't stop, and that means our domain is -∞ to 4, and our range is -2 to infinity, because of the arrow. It's increasing where it's red, it's decreasing where it's green, it's constant on that little shelf there where it's purple, and we have a local max at 1, 1. And then where we have a local min, it's a little bit more interesting. Again, because we have that little plateau, and so the min is a y value, but it's on a range of x values. And from that, we look for our extreme values. There's no absolute max because of that arrow, but there is an absolute min. Okay, for our last example, we've got an asymptote here. Again, notice the arrows that go up against the asymptote there. So if we're talking about the domain, we have to exclude 1. We have to exclude the little region in between for our range of values. And it's increasing everywhere. It's decreasing nowhere. There's no local max because that arrow just keeps going and we don't consider the endpoints. There's no local min. There's no absolute max. There's no absolute min.